Bismillahirrahmanirrahim. This is week number 15 for the online lectures on wireless communications. So today we'll talk about a very interesting topic about capacity of fading channels. We have already discussed on capacity of AWGN channels. How to find out the capacity of the fading channel. The fading channel can be represented in a very similar way as the AWGN channel. So if we just multiply the AWGN channel with a random channel response, we have the fading channel. So if we multiply GL with XL, then we have a fading channel in which XL is given by CN0Q and GL is the channel response. So there are two categories of fading channels. One is slow fading, one is fast fading. What is slow fading? In slow fading, the channel response takes one realization during communication. It means that when you transmit some data symbol before it and when the data symbol reaches the receiver, it has gone through or being multiplied or XL is being multiplied with any one realization of channel response. So for the whole transmission, for the whole L, G remains the same. What is fast fading? In fast fading, you have transmitted many data symbols, but different data symbols they experience different realization. In the ideal case, they experience all the realization during communication before reaching the receiver. So reality might be somewhere in between. Actually, the channels are neither slow fading nor fast fading. They are somewhere in between. So in slow fading, we have fixed channel GL is equal to G for the entire transmission. The assumption here is that receiver knows G, but the transmitter does not know G. Now the capacity for a realization CG is given by log 2 of 1 plus G square into SNR, where SNR is given by Q by naught. G square, G is the channel response, so G square is the channel norm. Capacity is defined by Cg is equal to log 2 of 1 plus G square SNR. So you can see that the capacity is basically a random phenomena because G is random realization of the fading coefficient. So Cg is also a random phenomenon. The transmitter does not know Cg. We have already discussed that receiver knows the channel H and it can calculate the capacity, but the transmitter before transmitting does not know Cg because it does not know the channel H. So no matter what the channel H, it cannot encode the data to achieve this capacity CG. Because the transmitter does not know CG or transmitter does not know the channel response, it cannot encode the data to achieve this capacity, or it cannot transmit at a certain data rate or that can achieve this capacity. So what we do opportunistic transmission. Now suppose the transmitter encodes. What is opportunistic transmission? Suppose the transmitter encodes using the data rate R bits per second. So two possible events can happen. If R is smaller or equal to Cg and Cg is random, you never know, you can have successful transmission. But if R is greater than Cg and you don't know Cg, so transmitter does not know Cg, you transmit at a rate which becomes greater than Cg, you can have large probability of error. So system is in outage if R is greater than Cg. Outage means that you won't be able to transmit anything reliably. So you won't be achieving capacity. So you won't be achieving that data rate. So when you transmit at that data rate, you would not be able to decode the data at the receiver. So that is called outage. So what we define here is outage probability for rate R because we don't have any other definition of CG here. So the best definition or best way of expressing this type of capacity in which we have outage, we can only find outage capacity. So for the case of finding the outage capacity, one needs to first find the outage probability for the rate R. And what is the outage probability for the rate R? It is the probability at a rate R in which the capacity is smaller than R, or R is greater than the capacity. So this is CG is smaller than R is the event of outage. The probability of outage event is given by the probability of CG less than R. Outage probability when G is equal to complex normal distribution 0 1. So the outage probability for rate R is given by V out R is equal to VR Cg smaller than R is equal to 1 minus e to the power 2R minus 1 of CR. So for relay fading case, we have found out the outage probability. This is given by this graph. So this is the area which is basically defining the outage probability. At higher SNR, this is approximately equal to 2 to the power R minus 1 over SNR. So outage probability decays with SNR is equal to Q over N naught as 1 over SNR. So now we define the outage capacity. What is outage capacity? Outage capacity is the difference from AWG in channel. So in this case in which the channel realizations are random, we don't have fixed capacity. So the probability of error cannot be arbitrarily 0. So only R is equal to 0 can guarantee 0 error flow. So in strict sense, the outage capacity or simple capacity is 0. So we define outage capacity. E outage capacity called CE. What is this thing? It is the largest rate such that P out R is smaller or equal to this epsilon. How do you interpret this notion? With probability 1 minus epsilon, we can communicate at CE with 0 error probability. So that is the interpretation of this outage capacity. That if we have E, then with 1 minus E probability, we can communicate at this capacity with 0 error probability. So outage capacity is defined by for relay channels. C is equal to log of 2 1 plus SNR ln of 1 minus E inverse. This part is the difference from AWGN channels because AWGN channel capacity is given by C is equal to log 2 1 plus SNR. So at low E, we are better with AWGN channel. With high E, we are better with fading channel. This is the graph you can interpret. Now, outage capacity with small outage probability. The fraction of AWGN capacity is given by this difference 1 minus E inverse. So much lower capacity than with AWGN channel. So this extra SNR value is the extra power you need for a relay fading case. So E is equal to 0.01, you have this graph, and E is equal to 0.1, you have this graph. Thank you.